When we design learning algorithms, there are several fundamental questions to ask about them. One is, what can be learned efficiently? So in other words, if somebody gives you a data set, how much time would you need with your algorithm to learn that data set? Another question is, what problems are inherently hard to learn? No matter what the samples for the data set are, maybe some problems are inherently hard. There is no algorithm that can solve them efficiently in terms of time. Another question is in terms of how many examples do you need to learn successfully, whatever successfully might mean in your context. And to answer these questions, you really need a framework that connects machine learning with computational complexity. And in this lecture and one more video after this one, I'm going to discuss one such framework. It's called the PAC learning framework, PAC standing for probably approximately correct learning. This is a framework that was introduced by Leslie Valiant in 1984. So there is quite a history behind this framework. And so in this framework, the way we start is, as usual, we have a set of examples, and I denote this as usual with a capital X. So this is going to be the set of examples. And then we have the set of labels. And as a matter of fact, in this presentation I do for PAC learning, I'm going to assume I have only binary labels. It just simplifies the discussion, and all of the things that we discuss here are valid also in the general case, and a similar discussion can be also done for regression. But just to simplify things, I'm going to assume that the labels are just 0 and 1 in our case. And I define now the notion of a concept, what a concept is. And the concept for us is going to be simply a mapping from the set of examples to the set of labels. And the intuition you should have is that this is the object that we are trying to learn. This is our objective, to learn a concept. So just to give you an example to fix this notion, set C could be simply the set of points inside the triangle. And so this would be very similar to what we had before in terms of examples. We had the example with family cars, and we were assuming that it's being defined by a rectangle defined in terms of price and engine power. And the class of family cars was characterized by the set of points inside the rectangle. So this is very similar. For example, C, a concept could be the set of points inside a triangle. And we also define the notion of a concept class. And I denote this by capital C, and this would be the set of all the concepts that we aim to learn. And so in our example here, the C could be the set of all triangles in a plane. And so with this notion, I can define then what's the notion of a learner. What does it mean that you have an algorithm that aims to learn? So we have this notion of a learner, and that would be an algorithm A. And this algorithm would have access to a hypothesis set So this is a hypothesis set, and what this is simply a fixed set of concepts. So you are going to have as an objective to choose one of the hypotheses, which is one of the concepts that you fix beforehand that fits as well as possible the data. The data is presented to the learner in terms of a sample distribution. So this is going to be a sample consisting of data points, let's say x1 all the way to xm. And these are samples which are independent and identically distributed according to some distribution D. And we also have, because we talk about supervised learning, we also have the labels. So the labels are going to be C of x1, C of xm. So one label for each data point. And this is the real label of this example. So the objective is going to be for your learner to select a hypothesis. And this hypothesis is going to depend on the sample you have at your disposal. So I'm indicating that with S. So select a hypothesis from your hypothesis set that has, and I put this in quotation marks and I define this in a moment, it has a small generalization error. With respect to concept C. And this generalization error can be defined in the following way. If we write it here, generalization error, so we are given a hypothesis and we are given a concept, and the goal is going to be for this hypothesis to approximate as well as possible, so with a generalization error that we define now with this concept. So that's the concept we try to approximate, and we also have the distribution that the samples are coming from. And so the generalization error this is also called very often the risk of H is defined as follows. This is often denoted by R from risk. So the risk of H is defined to be the probability mass when you have X sampled from this distribution D of this function, whether H of X is different than C of X. So this is very similar to what we had before in our examples. We were looking in how many cases the prediction of the model, which would be in our case H of X, is different than the real label of X, which is C of X. And this is the same thing as the expected value over X distributed according to D of this one function, one applied to H of X different than C of X. And so I just write this down. So this one function is defined as one applied to some property P, has values 1 and 0 depending on whether property P is true or false. And then we also have, because the difficulty with this is that obviously we don't have access to the concept and we don't really know the exact distribution D, we only have access to some sample of examples taken from this concept according to distribution D, but we don't have direct access to C and D. So that makes difficult to calculate exactly what the risk of H is. But we can do something else, and that is we can think about the empirical error. And the empirical error is, again, we have access to the hypothesis, and there is this concept in the background, and we have this sample that's we have access to, and then we define the empirical error or the empirical risk of H. This is defined as you might expect. So I'm using R hat just to indicate that this is empirical error, and this is something that depends on the sample, so I'm indicating that with S. So applied to H, this is simply going to be the average error this hypothesis makes. So it's going to be the average over M data points, so it's going to be 1 over M times, and we have here sum from 1 to M of the one function applied to H of xi being different than C of xi. So in other words, we are just measuring for each one of these data points in our sample whether the prediction of the model is different than the real label on that example, so whether we have an error in this data point, and we sum this up and we divide to the number of points in the sample. So this is the usual way the empirical error is defined. And it's not difficult to see that the expected value, so I'm just writing here, it's not difficult to see that the expected value of this empirical risk, when you take it over all samples distributed according to D to power M, because we need M data points, this is in fact going to be the risk of H. So in other words, what this means is that the empirical error is going to be, as an expected value, is going to be a good approximation for the generalization error or the risk of H. So with all of these definitions in place, now we can define what does it mean for a concept to be a PAC learnable. And this definition is going to be in terms of computational complexity. So it's going to be all about what can be learned using bounded resources. And so for that, I'm going to just denote by N the computational cost of representing any data point. So for example, this would be if you have a data point that has two features, it's going to be the space required for those two features to be saved on your memory. And then we also take into account the size of the concept. So we think about how much space do we need to represent the labels. So that's going to be the maximal cost of the computational representation. Of such a concept C. And finally, we also, just to fix this one more time, so HS is the hypothesis learned based on the sample set S. So with all of these things in place, I can now give the main definition, and that is so we will say that a concept class C is PAC learnable if we have, so there is an algorithm or a learner A, and there is a polynomial function, and I will define this in just a moment in all of its parameters. It has 4 parameters, and I come back to this in just a moment. So there is a polynomial function in these 4 parameters in such a way that for all epsilon larger than 0 and for all delta larger than 0, and also for all distributions D on the sample set X, and for any concept C, we have the following holding. For any sample of size M, which is at least this polynomial function, and here I'm writing the argument. It's a polynomial function in 1 over epsilon, 1 over delta, n, and size of C. So what needs to hold is that the probability over all samples distributed according to d to power m of the risk of this hypothesis being less than epsilon is at least 1 minus delta. And I comment in just a moment what this means exactly. So what you want to have in this notion of PAC learnability is that you have some guarantees in terms of how many samples do you need so that you are learning successfully. And here is what successfully means. You would like your learner to be approximately correct. And what that means is that this risk, so in other words, how far away is it from the real concept, how many mistakes in some sense it makes, you want this to be bounded. And this would be any bound you choose. So for any epsilon larger than 0, you want to be arbitrarily close to the correct answer. So this is the approximately correct part in our concept. So you would like to learn something which is approximately correct with a bound of approximation which can be made arbitrarily small. So you want to learn approximately correct, and you want to learn with with probability, or if you like, with confidence, which is arbitrarily high. And that's where this larger than 1 minus delta is. You want to be arbitrarily close to 1. You want to have arbitrarily high confidence in your learner. And this is where the probably part in our framework is. So to say it one more time, what you would like to have is a way to choose a hypothesis, and you would choose it in such a way that it's approximately correct and it's probably correct. So you can come as close as you want to the real concept, and you can have as high confidence as you choose to have. And the only question is, how many samples do you need to achieve that? And so if the concept class C is PAC learnable, then you will only need a number of samples which is polynomial in n, which was the computational cost of representing your samples. It's a polynomial in the size of the concept, and this makes sense because the more complex this concept is that you try to learn, the larger the number of samples is going to be, but it's not going to grow more than polynomial in that. And then you have these arguments 1 over epsilon and 1 over delta, and the reason for this is the more ambitious you become, either in terms of your approximation bound, you want to get closer and closer to the correct concept, or in terms of the confidence you have in your learner. Either way, you are going to pay a cost. The more ambitious you become, you are going to pay a higher cost, but that cost grows only polynomial in terms of 1 over epsilon and 1 over delta. So I would argue that this is indeed what you would, this would be a natural concept for the idea that your learner considers the computational cost of all of these ingredients going into it. And one more thing here is that if your algorithm A, so I'm writing here, if A, so your algorithm runs in polynomial time, and polynomial time with the same argument, so the polynomial in 1 over epsilon, 1 over delta, n and size of C, then we would say that this concept class that you looked at, so C is said to be efficiently PAC learnable. So efficiently standing for the fact that you can do it in time that only grows polynomial in terms of either the size of your complex or in terms of the ambitious level you are placing on your concept. So it might look quite a technical framework and maybe far removed from the real life, but I would like to show you in the next video an example of how to establish the PAC learnability of a concrete example. So we have an example in the next video.